This is a presentation of the paper entitled Extremum-Seeking Control Strategy based on the super-twisting algorithm to be presented in the IFAC World Congress 2020 in Berlin. The outline of the presentation is as follows. Now, extremum-seeking control is a model-free real-time optimization tool applicable in situations where there is a nonlinearity in the optimization problem. And such nonlinearity has a local extremum, might be a minimum or a maximum. The nonlinearity may be in the plant as a physical nonlinearity or in the control objective as the objective function. Classical extremum-seeking control aims to find an optimum input for generally unknown objective functions or input-output maps in steady state and uses a jitter signal to prove the input-output map so as to estimate the gradient of this map. In this century, due to the robustness properties against model uncertainties, sliding modes have been considered to propose robust extremum-seeking algorithms. In particular, in the last decade, several articles have been proposed to address the extremum-seeking problem via sliding modes. In this presentation, a super-twisting-based extremum-seeking control algorithm is proposed to bypass the uncertainties in the input-output map. First, information about the control input and measure output is used to estimate the gradient, which is used then via the optimization algorithm to compute the online optimum of the control input. Now, as for the problem formulation, let us consider the following dynamical system. It's a state space model with n states and with just one input and one output. Furthermore, let us consider a unimodal function L, which maps the output in steady state. So in this slide, the optimization problem to be solved is as follows. We want to maximize L given that L is the output and the output is given by this dynamical system. In order to do this, we adopt the following assumptions. We consider that L is twice continuously differentiable around the unique maximizer it has. It might be a local maximizer, but it has just one maximizer, which we denote by U star. Now, in order to compute the control input that maximizes the input-output map in steady state, let us begin with an initial condition for the control input. To compute the next value of such a control input, let's just adopt this value here. This value here is just a constant which multiplies the gradient of the input-output map. So this gradient is the direction, is the value in which the input-output map grows quicker. Okay, given that, let us now define alpha sub d as in this fashion, and let us just rewrite the expression above in this way here. When we make delta t, which is the time step, very small, we get here a law for updating the control input. Now, although it seems that the previous control law solves the problem, it has the issue that we have to know the value of the input-output gradient. In order to overcome this issue, let us not consider that input-output gradient, the value of that input-output gradient, but let us just consider its sign, which is just a function which is +1 or less 1, right? This control law, which we have here, it induces a first-order sliding mode. So, this motivates us to consider this term here, which is a second-order sliding mode, which precisely the super-twisting algorithm. Here, lambda and alpha are positive constants. By considering the sliding variable to be as the negative of the gradient, this algorithm asymptotically maximizes the input-output map in steady state. Please notice that the super twisting algorithm includes a proportional action and an integral action. By considering the sign of the gradient in both terms, the robustness of the optimization algorithm is enhanced. On the other hand, the square root term in the proportional term acts as an adaptive gain. Since the initial condition is in the neighborhood of the optimum control input, normally the slope of the tangent line in each point on the objective function is less than 1. Hence, the square root term assures that the control input u will approach to the optimum value faster than the nominal control input u1. In order to use this control law, we need to estimate which is the gradient. Now, to estimate the gradient, we will use this differentiation strategy, which is called the parametric differentiation. If I want the partial derivative of y with respect to the partial derivative of u, I can divide the derivative of y in time to the derivative of u in time. This is called the parametric differentiation. So if I wanted this estimate, one way to do it is just to estimate each one of these derivatives, right? In order to do so, let us consider this vector, which has the output measurements and the computed inputs, and we want to estimate these derivatives, right? The way to do it, so we will use this differentiator, which is based also in the super twisting algorithm. So this is a multivariable differentiator. It also is finite time robust stable. So it finds the estimate of the first derivatives in finite time. One way of choosing the functions phi1 and phi2 are these. And what I input to this algorithm is the difference between the actual measurements and the estimated measurements. And what do I need for this algorithm to converge? What do I need is only to form this matrix, right? And once this matrix is formed, I just have to design the constants k1 and k2 so as to make this A matrix Hurwitz. Okay, up to now we have designed a control strategy based on the super twisting algorithm that is capable of conveying the input-output gradient to 0, hence converging to the maximum. Right? That strategy requires the estimation of the input-output gradient. As we have seen, that input-output gradient is obtained by a differentiator, which is also based on the super twisting algorithm. In order to show the applicability of this strategy, let us consider a microalgae production process modeled by a system of 3 ODs. The state variable S represents the substrate in which the culture is growing. The state variable Q represents the minimum quota of substrates needed for the cellular growth, and the state variable X represents the biomass concentration in the control medium. In turn, S in and Q in represents respectively the concentration in the renewable medium and the flow rate of the renewable medium. Here the functions ρ represents the substrate uptake and growth rate respectively. The function ρ is a monod-like function, meanwhile the function mu is a droop function. Now, the control problem that we have at hand is the maximization of the productivity of such a reactor. By productivity, we mean how much biomass we are getting from such a reactor. Right? The quantity of biomass that we are getting from such a reactor, we can compute it in this way, right? Which is the concentration of the biomass divided by the volume and multiplied by the input-output rate. So, now, to assess the performance of our design strategy, we do require to know where the optimum is. So, by means of the computation of the steady states, we can compute which is the productivity of the reaction rate as a function of Qin. Right? We can work out the maths, and it has these forms in which all the A's are constants which depend upon the parameters of the system. In order to obtain which is Q star, in this case, this is the value which maximizes the productivity, we can differentiate and equate to 0 this expression, and we thus obtain the maximum productivity, the maximum productivity, which would be this one, and which is the input required to obtain that maximum productivity. Now, these are the conditions for simulation. We perform all the simulations in MATLAB. We use a constant substrate concentration in the renewable medium. And for the classical extremum-seeking control, we use an optimization period of 2 days. Whereas for our proposed algorithm, we are using an optimization period of 5 days. That is, every 2 days for the extremum-seeking control, I have to update the input, and every 5 days I have to update the input for the super twisting based strategy. Here we have the set of parameters that we are considering. And on W is the frequency of the dithering signal for the classical extremum seeking. WH is the frequency of the high pass filter frequency. A is the amplitude of the dithering signal, and chi A is the size of the optimization step. We consider 2 sets of parameters for the extremum seeking control based on the super twisting algorithm. One with large values for the optimizing part of the algorithm, and one with smaller values relatively. Now here are our simulation results. The red curves are regarding for the extremum seeking control, the blue curves are for the fast extremum seeking control based on the super twisting algorithm, and the cyan curve is for the slow super twisting based algorithm. As we can see, all of them converge to the optimal point. However, the fast super twisting algorithm converge faster than the classical extremum seeking control, with the amplitudes of the oscillations around the optimal point, which are similar to those of the extremum seeking control. However, if we have a slow convergence for the extremum seeking control based on the super twisting algorithm in the cyan curve, we can see that the oscillations are rather small. The same observations yield for the productivity. All of them attain the optimal point with larger or smaller amplitude of oscillations around the origin. Here we see the gradient estimation. So the most important thing regarding the gradient estimation is that the super twisting based strategy actually computes the gradient by means of differentiation, where the extremum seeking control does not compute the gradient, but it just filters some signals to obtain an estimation of the gradient. It is also remarkable in this graph, in the objective function, how they perform tracking the objective as it moves. I mean, how the productivity moves regarding the input of the algorithm, the input to the system. We can see that the extremum seeking, the classical extremum seeking, and the super twisting based control, they ripple around this objective function, right, with a rather large amplitude. However, the slow extremum-seeking tracks very well the objective function, right? However, it does present a slower convergence time. So there is a trade-off in the design of the parameter values. Here I have some conclusions of our work. Time is running out, so I will leave it here. Please, we will be happy to follow the discussion as by any means possible. Thank you very much.